Here is the HNMR spectrum of allyl bromide. Let's see how to interpret this spectrum. In an allyl bromide, you have 4 different types of protons. We have A protons, B protons, C, and D protons. The B and C protons right here, they are actually non-equivalent protons. Although they are present on the same carbon, they are going to be non-equivalent because one of these hydrogens, the B protons, is actually in trans configuration with respect to the CH2Br, and the C protons is actually in cis configuration with respect to this group, and therefore they are said to be non-equivalent protons, and they are going to have geminal coupling. Okay, now let's see the splitting pattern that exists in this compound. Okay, we'll take the A proton first. The A proton has actually one neighboring proton. If you look into this carbon, this is the neighboring carbon, adjacent carbon, and you have only one hydrogen, and the splitting pattern is going to follow n plus 1. Our n is going to be 1, and therefore it's going to be 1 plus 1, which would be a doublet, and you can see the doublet right here. Okay, let's go on to the D protons. The D protons are actually going to be split by B, C, and as well as A, and therefore you can see that there is a multiplet that exists about like 5.9 delta value. The B and C protons, they are both non-equivalent, and what happens here is the B protons will be first split by the D protons as a doublet. Okay, remember our value for n equals 1, and it's going to be n plus 1, which would be doublet. So you will see a doublet first, and this doublet will again be split by the C protons, which would look more like a doublet of a doublet, something like this. Okay, and the same thing is going to happen with the C protons as well. The C proton will first be split by the D protons, and again that doublet will again be split by the B protons. So on the whole, you will be getting 2 doublets of doublets, one for B proton, another one for C protons, which you can see right here. Okay, because this is geminal coupling, you will not be able to see the actual doublet of doublet in here. It will, the coupling constant is going to be really small, so you might just see as doublet. Okay, so this is going to be for B proton, and this is going to be for the C protons. And if you blow up the spectrum, you should be able to see the doublet of a doublet. There is distinct difference between chorded and doublet of doublets. On the left, you have a chorded, and on the right, you have doublet of doublets. You can see in the chorded that the peak intensities are actually in the ratio 1:3:3:1, whereas in doublet of doublets, all of the peaks are going to be of the same intensity, and it is represented by 1:1:1:1. Okay, so you can obviously note the difference between chorded and doublet of doublets.